In this video, we're going to talk about the parallel axis theorem as we continue our discussion of moments of inertia. The parallel axis theorem relates the area moments of inertia of around the x-axis, the y-axis, and the polar moment of inertia to some centroidal area moment of inertia. That's currently what we have going on right now. But maybe we want the moment of inertia about some other random axis, and that's what this parallel axis theorem allows us to do. So if we look at this image over here of this pear-shaped object, typically we can find the moment of inertia about the centroid, and a lot of times we want to do that, but there are also times we want to find the moment of inertia about the x or y axis or some other random axis around here. So what we do is, let's say we want to find the parallel or the moment of inertia about I sub x. We can easily find the I sub x around the centroid, that's this prime one, and then we add to that the distance squared, that's the distance to the x-axis, times the area. Okay, so these are the key part here is to note that this whole section is the moment of inertia about the centroidal axes. The other good thing about this is it allows us to use something called composite shapes. Otherwise, we'd have to use the methods of integration that were discussed in section 1, but I want to concentrate more on using composite shapes, because a lot of the shapes that we use as engineers are very simple shapes like I-beams, T-beams, rectangular beams, things like that, as opposed to parabolic type shaped cross-sectional beams. We are very fortunate that in the back of our book, many engineers have produced, again, these tables that are in the back of the book. And again, we've used these tables primarily for finding the centroid of an area. But now we can use these tables, and we'll discuss these more down here, to find the moment of inertia about different points. If we look at this I prime, the prime one is always through the centroid. Some of these shapes have just the IX and IY, which are to the axis given in the diagram itself. Some of them, like circles and circular shapes, do not have them. But there are times also that we may want to find the moment of inertia about some other axis on here. Okay, so that's where the parallel axis theorem really comes in handy. So like I mentioned, I've already really answered this question, what is it good for? It's usually that we want to know the moment of inertia for an area about a centroidal axis, and the parallel axis, like we know that already, but we want to know it about some other axis that is different than that one. So as an example, we may have some beam shape, a T-shaped beam, and we want to know what it is about this x-axis for some reason, okay, given some maybe y-axis type thing here. So the other thing that this parallel axis theorem does is it allows to remove the restriction that we had using the method of integration. I'm not going to really go into that so much, but really spend more time again on this composite shape. So now we can build up beams like a T-beam like this, and maybe we will know, of course, our x prime and y prime for a particular beam. So for each composite shape, we'll know, like this one here, we would know it also for, we'll call this 1 for shape 1, and then for shape 2, here's our x2 for shape 2, because it goes through the centroid itself. So that's the same one there. But maybe we want to know where it is relative to this axis down here, this x-axis down below. How do we actually use this parallel axis theorem for that? So again, we can do this for both the moment of inertia about the x-axis, the moment of inertia about the y-axis, and then the polar moment of inertia. And we're just really going to concentrate in 2 dimensions for this class and most things that we will need. What I will be doing is I will go through a couple examples So please take time to look at those examples.